Hello and welcome. We're about to dive into one of the most mind-bending paradoxes in the entire history of physics. It's a wild story that kicks off with a tiny, imaginary creature and ends up completely changing how we think about information itself. Seriously, it reveals this deep, physical link between knowledge and energy that is just, well, it's fundamental to everything.
So let me just ask you this. Picture a law of nature so basic, so woven into the fabric of reality, that everything from your coffee cooling down to the expansion of the entire cosmos has to obey it. Now, what if I told you that over 150 years ago, a physicist dreamed up a creature small enough and smart enough to flat out break that very law?
Okay, so before we meet our little culprit, we've got to understand the law it supposedly broke. And this isn't just some minor regulation, you know? This is a pillar of physics. It basically dictates the arrow of time and the fate of the universe. It's called the second law of thermodynamics. Now, the law itself sounds pretty straightforward. Basically, it says that left to their own devices, things get messy. The official term for this messiness is entropy. So think of a brand new ordered deck of cards that's low entropy. Shuffle it once and boom, entropy goes way up. The other big part of the law is that heat only ever flows one way, from hot to cold, never ever the other way around on its own. And this is the perfect example, right? You leave a hot cup of tea on your desk, and what happens? It cools down. It gives its heat away to the colder air in the room. You would never in a million years expect the cool air to spontaneously gather energy and heat your tea back up. It just doesn't happen. The universe has a one-way street for energy, and the second law is the cosmic traffic cop.
All right, let's get to the crime scene and meet our prime suspect. Back in 1867, the absolute genius physicist James Clerk Maxwell cooked up a thought experiment. He imagined a tiny, super intelligent being, he called it a demon, that could seemingly get around the second law. Now, this wasn't a real creature, of course, but it was a powerful idea designed to push the boundaries of what we thought we knew.
So, how did this demon supposedly pull off its impossible trick? Well, picture a box filled with gas, and it's all one uniform temperature. Our demon is sitting at a teeny tiny door and a wall that divides the box in two. As all the gas molecules are zipping around, the demon just watches them. If a fast, hot molecule comes from the right, it quickly opens the door and lets it into the left side. If a slow, cold one comes from the left, it lets it pass to the right.
So after doing this for a little while, guess what? The demon has sorted all the molecules. The left side of the box is now hot, and the right side is cold. It has literally made heat flow from cold to hot. It created order from a disordered uniform gas. It has decreased the total entropy of the system. And it did all this without doing any work itself, just opening and closing a tiny weightless door. It's a perfect, clear-cut violation of the second law.
For decades, this paradox just stumped everyone. The demon seemed to have a perfect case. But then, in 1929, a scientist named Leo Szilard found the first major clue. He boiled the problem down to its absolute simplest form, a one-molecule engine. And in doing that, he pointed the finger at a totally new suspect: information. This was the very first hint that knowledge itself might have a physical price tag.
Okay, so let's check out this brilliant little setup. This right here is Szilard's engine. It's just a cylinder with a single, lonely gas molecule bouncing around inside. By taking Maxwell's whole box of gas and shrinking it down to this, Szilard could zero in on exactly what the demon was doing. That felt like magic.
So, here's step one. The demon slides a partition right into the middle of the cylinder. Then, it just looks. It just checks to see which side the molecule ended up on. And this is the crucial moment. By looking, the demon now knows something it didn't before. It possesses one single bit of information. Is the molecule on the left, or is it on the right?
And now for the payoff. Because the demon knows where the molecule is, it can put that knowledge to work. It attaches a piston and a little weight to the side that has the molecule. That single molecule, as it bounces around, will push on the piston, lifting the weight and doing real, actual work. This whole process pulls in a little bit of heat from the surrounding environment and turns it directly into useful energy. It's seemingly getting a free lunch from the universe.
Szilard's big insight was that the solution had to be tied to that moment of gaining knowledge. He was the one who proposed that the act of measuring, of getting that one bit of info, must have a physical cost. He argued it had to generate at least as much entropy as the work the engine produced, perfectly balancing the cosmic books and saving the second law. And you know,
For a long, long time, that was the accepted answer. People thought, okay, problem solved, the cost is in the measurement. It was a tidy explanation, but it turned out to be wrong. It was a classic red herring in our detective story, and the real culprit was still hiding right under everyone's noses.
The case wasn't really cracked until much later, in the second half of the 20th century, thanks to physicists like Rolf Landauer and Charles Bennett. They looked at the demon's entire operation and had a huge realization. Everyone had been focusing on the wrong step. The real cost wasn't in learning something, it was in forgetting it. And that idea has massive consequences for every single computer on Earth. So, here's the key. For the demon to work like a real engine, it has to run in a cycle, over and over again. Think about it. After it uses the information about the molecule's position to do some work, it has to clear its memory, right? It needs a blank slate to be ready for the next molecule. The real thermodynamic cost isn't in writing the information to memory, it's in the unavoidable act of erasing it.
This is what's known as Landauer's principle, and it is a truly profound idea. It says that information isn't just some abstract concept floating around. It's physical. And because it's physical, getting rid of it has a real, non-negotiable cost. To reset a memory bit to a default blank state, you have to release a minimum amount of heat. And this isn't just theory. It's a fundamental reason why the gigantic data centers powering our digital world get so incredibly hot. This shows us exactly why erasure has a cost. Just look at the top row there. The memory can start in one of two possible states, right? L or R, representing a 0 or a 1. To erase that bit means you have to force it into a single standard state, in this case, L, no matter where it began. You're physically going from two possibilities down to just one. You are reducing the system's uncertainty, and that is a physical process that takes energy. Let's just walk through it real quick. Imagine the demon's memory is like that 𝘂𝗧 engine again. To erase it, first you take out the partition. Now the molecule could be anywhere, total uncertainty. Then you use a piston to physically squeeze the chamber back into that one standard half, the blank state. Well, pushing that piston requires work, and that work gets converted directly into heat, which gets dumped out into the environment. And here it is, the beautiful solution. The absolute minimum amount of work you have to do to compress that gas, to erase one single bit of information, is exactly kT log 2. And guess what? That is the precise amount of energy the demon got out of the system in the first place. It all adds up perfectly. The books are balanced, the heat released by forgetting completely cancels out the order created by knowing, the second law is safe and sound. So, what's the big deal? Why does a 150-year-old thought experiment about a make-believe demon even matter today? Well, it matters because in solving this paradox, physicists stumbled upon a fundamental connection between the laws of heat and the laws of information. And that connection sets the ultimate hard limits on the technology that powers our entire modern world.
What Maxwell's demon taught us is that information isn't just an idea. It's not ethereal. It's physically encoded in the world, and messing with it has real physical consequences. Every single time you delete a file from your computer, or a program resets a variable, or your phone clears its cache, a tiny but very real amount of heat gets generated. Landauer's principle defines the absolute bare minimum energy any computer will ever need to run. It is the fundamental speed limit, the ultimate boundary for computing efficiency. And that leaves us with a pretty fascinating question to ponder, doesn't it? If the simple act of forgetting has a physical cost, dictated by the laws of thermodynamics, what other aspects of our consciousness, our thoughts, our memories, are fundamentally tied to the very laws that govern the cosmos? It's a powerful idea to think about. Thanks so much for joining me on this deep dive.